Yes, sir. ENGR 272 students, we're back at it. Now we're going to start looking into basically parallel networks and how we can actually solve for the inductor current or the capacitor voltage. And we're just like with the series elements, we're going to be looking at the different forms of the differential equation that we either derive directly from the expansion of the KCL equation into basically all voltage, because remember parallel elements share the same voltage, or we're going to be looking for the inductor current with the substitution method. That's what we're going to really specifically look at today. This is on page 24. This is example 1 for the parallel networks. And so two things that we're actually going to see, it's a little bit different from what we've investigated with the series elements. This time we're actually going to see a final steady state condition for the current through the inductor at t is equal to infinity. And we're also going to be considering this underdamped response in which we're actually going to have oscillation within that transient period to where that oscillation is actually going to render a final current of 2 amps directly. So we're going to see how this works, and this one's a little bit lengthy. It definitely takes up a full 3 whiteboards in order to actually get it done. But, you know, throughout these 6 problems that we're looking at, 3 for series, 3 for parallel, is that we're kind of looking at all of the different variations that we can actually see, different derivations of the equations, and how those vary between series and parallel, and how that actually also affects the characteristic equation and the coefficients within the characteristic equation. And then we're actually seeing, overdamped case, underdamped case, and also critically damped case, and basically how to solve those when we do the partial fraction expansion. So this one we're actually going to take a look at the underdamped case, and actually for most people I see this confuse my students, and they see an exponential multiplied by a sinusoid and they think, oh, this is hard, this is so hard. It's not any more difficult than dealing with basically an overdamped or a critically damped case. There's a little bit extra work that you have to do, but the nice thing is that the book is actually, in the circuits 1, well actually just circuits 1 and circuits 2 book, they actually set up the partial fraction expansion very, very easily for us. So there's only a couple of things that we have to do extra, but it's generally the same process. So let's take a look at this one. Now I like this problem because there's a couple of extra things that we're doing here. We're going to be utilizing source transformation, and readily, this doesn't just look like a parallel network, but we're going to see how it's going to evolve into something that we can solve with KCL and the expansion of that with the current voltage characteristics, and then maybe a little bit of substitution. Now, if you remember correctly, and by now you guys should have gone through and practiced how to derive these differential equations in all the forms by basically either series or parallel. So obviously with series we utilize KVL, with parallel we use KCL. So by the time we get over to the right hand side of the board, part of this you guys should just have readily available in your heads, especially with the substitution method. So let's take a look first at the initial conditions. Obviously, initial conditions, that's for t less than 0, in which the capacitor is acting like an open circuit and the inductor is acting like a short circuit. So this one, I went ahead and just did a little source transformation. Bring that back. A little bit of source transformation in which we took basically the 150 volt source, basically converted that into a 10 amp source by dividing 150 by 15. Take the 15 ohm resistor, we put that in parallel with 25. Bam, in parallel, that gives us an equivalence of 9.375 ohms. Now, if we look over here, guys, check this out. We got a short that's been introduced in the middle of this network right here. So that short is actually going to drive very, very cool things to happen here. Number one, it's going to drive that open circuit right there. It's going to drive that voltage across the capacitor to be 0. Got a short has a voltage of 0, and that's going to be in parallel with the capacitor. That means the capacitor is going to have 0 volts. 2.7 ohm resistor is not even going to matter. And here, that 2 amp source is just going to see something, an element that's substantially less resistance, and it's going to dump all that 2 amps into the short. But what about the current that's being provided by the 10 amp source over here? Well, if we consider the fact that whatever current splits between 9.375 ohms of resistance and 10 ohms of resistance, that current that goes through the 10 ohm resistor is just going to flow. It's going to get to the capacitor and say, nah, not even going to deal with it. It's open circuit anyway, doesn't matter. But main reason why that is 0 volts for that capacitor is because no charge is going to it. No charge is going to it because that current through the 10 ohm resistor just bypassed it. Oop, now it got to the 2.7 ohm resistor. No, don't even want to deal with that either because you got 0 ohms on this side. And so that current's just going to go and bypass the capacitor, get to the resistor. Not even going to worry about that either. And then it's going to just dump right into that inductor and combine with 2 amps. And that 2 amps is going to cycle back around. And here, that current in steady state is actually going to come back around and then regain to form that 10 amps over here. So, in this case, it's very, very simple to find that initial current. The current going through the inductor is the same as the current going through the 10 ohm resistor. It's because of how this resistor was actually, this inductor was acting as a short. If there was a resistor in series with that, that would change the game quite a bit. We have to do a couple of extra things, and then we would actually see some current go to the 2.7 ohm resistor, and we'd actually see a different voltage applied across the capacitor. But because we're treating the inductor as an ideal inductor, we're not going to consider its internal resistance, so we're just going to go ahead and just model that directly as a short. Now, finding that is very, very simple. IL of 0 minus is equal to 10 in bicurrent division times 9.375 over 9.375 plus 10. And we're going to add on that 2 amps over on the left-hand side. That's going to give us a total current, initial current going through the inductor at 6.839 amps. Now obviously VC of 0 minus is equal to 0 volts. So remember though that when we consider having a second order differential equation, we need not just one initial condition, we need 2 initial conditions. So once again, we're going to look at what happens here. The switch opened at t equals 0. Once that opened, this 150 volt source or the 10 amp source, whichever way that we're actually equivalently modeling those, that it's gone. It doesn't even exist. So t equals 0 plus, then we can easily say, just as we've said over and over and over, that inductor's current can't instantaneously change. That capacitor voltage can't instantaneously change. So at IL of 0 plus and VC of 0 plus, they hold the same values for that instance after that switch is open. That magnetic field prevents basically that current from instantaneously changing. The electric field within the capacitor prevents that voltage from instantaneously changing. But how do we deal when we consider finding the inductor's current with parallel networks? We're going to have a second order differential equation, so not only do we need to have IL of 0 plus, we also need to have the rate of change at which we will have IL of 0 plus basically, that rate of change in which it's going to maneuver away from that initial value. So DIL of 0 plus dt, just as we did before, we're taking a look at basically evaluating that current voltage characteristic. You guys should have those memorized in your head by now. And that's equal VL of 0 plus divided by L. That's just that current voltage characteristic evaluated at t is equal to 0 plus. So in this case, because parallel elements have the same voltage, we know for a fact that VL of 0 plus divided by L is also equal to VC of 0 plus divided by L. And that's equal to 0 volts divided by L, and that's equal to 0 volts per, that should be 0 amps per second. Ooh, man. May have to get a point on an exam for that one. Oh man, I messed up. All right. Now, a couple of things here that I find very, very fascinating. I love this part of the discussion here. Because really what happened is that the inductor in steady state had a voltage of 0. Okay? That drove and caused this capacitor to not receive any charge. And if it doesn't receive any charge, it's not going to have a voltage. It's not going to have positive and negative. It's not going to have that potential difference built between the anode and the cathode. Once that switch opens, because of the fact that that capacitor cannot instantaneously change its voltage. It's going to latch this guy over here. It's going to latch that inductor to hold to 0 volts. Remember that inductor can actually change that voltage instantaneously, but it's going to latch that inductor to actually hold to 0 volts right here. And because of that, that renders the change in the initial condition to actually be 0 amps per second. So now we actually can see how we have this kind of like reciprocating effect between the inductor and also because of the capacitor. It's so cool, like how that works out, how one drives the other to have a value for t less than 0, but once that switch opens, kind of holds it to that value, saying, no, you hold me to 0 volts, I'm going to hold you to 0 volts at t is equal to 0 plus. Okay, so now we have these initial conditions. Let's actually start solving this problem. Now, for parallel elements, finding the inductor's current, we are actually going to have to use the substitution method. We're going to have to take basically the KCL equation, we're going to expand it by the current voltage characteristics, and we're going to substitute in that current voltage characteristic to put and manipulate the entire equation all in terms of IL of T. So let's do that. Let's take a look. Now you guys should be good to go on this. Should be practicing this up front. So we're going to move quickly through this. All right. Let's see here. Board number 2. Here we go. All right, guys. So 2 amps. Once that switch open, right side of the circuit, bam, gone. So 2 amps, and we got the inductor in parallel, the resistor in parallel, and also the 10 millifarad capacitor in parallel as well. Now, obviously, I said this in the book that these values that I've utilized for all these examples are not necessarily general values that we use for capacitance or inductance, but they're utilized to basically prove points and teach you guys how to actually solve these types of networks. But 10 millifarads, that's a lot of capacitance. So we see it in terms of microfarads. But let's go ahead and start solving this system here. Now we obviously know intuitively, remember we have to be thinking about what we think is going to actually happen in the long run anyway with these circuit diagrams, because once we get to the very, very end, we shouldn't just say, oh yeah, I just did my calculations there and I think it's correct, therefore there it is, and obviously it's going to be correct. No, you should be checking your solution and see if your solution makes sense. Now, looking here, we have a 2 amp source. And that 2 amp source is going to drive a final steady state value of 2 amps through that inductor. So I know at the very end of my calculations that I should have a transient state. That's going to be of an exponential form in this case because it's underdamped. It's going to be exponential and have oscillation within it. And then we're going to have a final steady state value of 2 amps that goes through that inductor at basically t is equal to infinity. So we should be watching at the very end and see if our calculations gives us that 2 amps, that steady state, that DC value of 2 amps. So by KCL, IC of t plus IR of t plus IL of t is equal to 2 amps, right? Okay. C dVCT dt, that's the expansion of ICT. IR of t, VR of t over R. IL of t is the variable that we need. Here we had 3 variables with 1 equation. So we're going to manipulate this equation by substituting in basically VC of t, VL of t, both being the same, and VR of t being the same. We can substitute in that VL of t is equal to L dilt dt. We can substitute that in basically for VC of t and VR of t because their voltages are the same, because they're parallel networks. And by doing that, oh, look what we got down here, just as you guys should have been practicing. Bam, we get it. Like enter here for basically VC of t, we get L dil of t dt. Take the derivative of that, multiply that by the coefficient of c right here, 1 over r. And then enter here for VR of t, we get L dil of t dt. And then IL of t on the side is equal to 2 amps. Guys, take the derivative of a derivative, basically get second order derivative, and then we take the entire equation, and by dividing through of LC, basically isolating the highest order derivative and putting that equation into standard form. D squared IL of t dt squared plus 1 over RC. Yep, we should be expecting that for basically this portion of the equation. DIL of t dt plus 1 over LC IL of t is equal to 2 over LC amps. Go ahead and we basically substitute our knowns in there for those values of the resistance, inductance, and the capacitance. Bam! D squared IL of t dt squared plus 37 DIL of t dt plus 1000 IL of t. Woo! That's looking pretty crazy. And then that's equal to 2000. Guys, got a problem here. We've got an underdamped case. It means we don't have enough resistance within the circuit. We don't have enough resistance to keep that thing from oscillating. We know it will eventually reach into a steady state value of 2 amps, but we're going to probably see an exponentially decaying oscillation into that. So if we look here, guys, we're going to be maneuvering from 6.839 amps all the way down to 2 amps, and during that exponential decay, we're going to see kind of some oscillation as it goes down. So, and we can immediately see that because we know that the characteristic equation from here, that would be s squared plus 37s plus 1000. We can't just readily factor that into real and distinct or real and repeated roots. So we actually have to say, oh man, we got something else that we got to do. But let's go ahead and take the Laplace transform. Let's put this thing into the frequency domain and then actually go ahead and solve for I of s. Then we'll worry about dealing with this characteristic equation in just a sec. So we take the Laplace transform, everything in purple, we're in the frequency domain right now. S squared times I of s minus s times I naught plus, minus I prime of 0 plus 37 s times I of s minus I of 0 plus 1000 times I of s, and that's equal to 2000 over s. So we go ahead and combine like variables. In this case, the like variable was I of s. So now we actually get our characteristic equation of s squared plus 37s plus 1000. Maneuver everything over onto the right side. Here we had s times I naught, so that's 6.839 amps. And then here we also had I prime, that was 0. But then 37 times I naught, that gave us 253. And then plus on. Don't forget, do not forget, when you got that condition over here, that steady state condition that we're going to expect to see, that when you take the Laplace transformation of a constant, do not forget over here that you have to divide that by s in the frequency domain. Otherwise, everything is going to be thrown off and you won't get that steady state value in your final solution. So we also have another problem. Because we have 2000 over s, that's going to make the solution for I of s in the frequency domain look really, really, really weird. Check this out. In the numerator, one of the sections of this equation, or the numerator portion of the equation, has an s that's being divided here. We can't have that. We need to get rid of that in such a way that we can actually start doing the partial fraction expansion. So here, 6.839s plus 0 plus 253 plus 2000 over s. We're going to multiply the top and the bottom by s. And when we multiply the top and the bottom by s, so that means s over s, that means that's equal to 1. That means we're manipulating this equation into an equivalent form. And when we do that, we get 6.839s squared plus 253s plus 2000. But on the bottom, we get s times s squared plus 37s plus 1000. And that we can actually do a partial fraction expansion on. And when we do that partial fraction expansion, we're going to see that we get a1 over s. And then in this portion, this is the form that I was talking about that's in the book. We get a squared times s plus alpha over s plus alpha squared plus beta squared plus a3 times beta over s plus alpha squared plus beta squared. Whoa, the heck is that? That right there, guys, to me, that looks like 1, 2, 3, 4, 5 variables that we need to solve for? Well, if you watch the video that we talked about, basically the partial fraction expansion, sure enough, alpha and beta squared we can find readily from the characteristic equation. We can find it from the characteristic equation. And we do that by completing the square. And once we complete the square, all we have to do is basically find A1, A2, and A3. But how do we complete the square? You guys should remember this from your math classes, but let's go ahead and give a refresher on that. Okay, let's move over to the next board. Completion of the square. And when we complete the square, that will actually give us our values of alpha and beta squared. The thing is that beta squared, beta itself is actually the angular frequency of the cosine and sine portions of the exponential, which is just amazing to me. That characteristic equation has that frequency in it that's going to oscillate at. So here we got s squared plus 37s plus 1000. All we have to do is, and once again, this is an equivalency. We're going to basically take this equation and manipulate it into something different. But it's 100% equivalent. So we're going to take 37s, we're going to divide that by 2 and square it, and leave this section in the inner brackets. But if we add on a term of 37 over 2 squared, we got to subtract that off in order to maintain that equivalency. So minus 37 over 2 squared plus 1000. So this portion is what's going to be on the outer bracket here. And then once we actually give this term here 37 over 2 squared, then we get s plus 18.5 squared minus 342.25 plus 1000. And then our final completed square of that characteristic equation is s plus 18.5 squared plus 657.75. So that means alpha is actually 18.5, beta squared is 657.75. So now we have the portions of this equation that we can go ahead and just substitute in, where alpha is 18.5 and beta squared is 657.75. And now we can start treating this expansion here just like we've done with any other partial fraction expansion. We've got to develop a system of equations so we can address A1, A2, and A3. And all we have to do is basically divide through by the completed square of this partial fraction expansion over here, and then we get 6.839s squared plus 253s plus 2000, and that renders basically all the denominators gone on the right hand side as well, because we get s plus 18.5 squared plus 657.75 times A1 plus s times s plus 18.5 times A2 plus s times 225.65 times A3. Here we go. Evaluate each of these. S is equal to 0, s is equal to 1, s is equal to 2. That means we get 3 equations, 3 unknowns. Throw this into our matrix once again. Row reduced echelon form will render us the values of A1, A2, and A3. And just double checking through intuition, A1 should have come out to be 2, just like we said earlier. Looking at that circuit for t greater than 0, we knew what was going to be driven to be that inductor current in steady state. And sure enough, there it is. If we got a value other than 2, something in our math was probably wrong. But here came out to be right. I've even made this mistake before where it came out to be something different, and as soon as I saw that, I was like, oh man, I got to go back and check my math, and sure enough, I punched in a number incorrectly. Imagine that, punching in something incorrectly in your calculator or MATLAB. Happens. But that's why we think intuitively about these things, because the math isn't always correct. We have to know what we're actually doing and apply basically that math in order to make sure that we are producing the correct answer in our analysis. So here, the final partial fraction expansion of I of s and its equivalency to the original form of I of s, 2 over s plus 4.84 times s plus 18.5 over S plus 18.5 squared plus 657.75. Notice here, we said this in an earlier video, we got 3.48, that was A3. Do not multiply 3.48 by 25.65, or basically what beta is. That's basically the square root of 657.75. Do not multiply those two together. It's a temptation to do, but that will give you the wrong coefficient of basically the exponential sinusoid. Here, this right here is the form that we're actually going to take the inverse Laplace transform on and actually gain that portion of the transient response. And sure enough, if we do that properly, we get IL of t is equal to 2 plus 4.84 times e to the negative 18.5 t. So basically that's e to the negative alpha t times cosine of 25.65 t plus 3.49, I kind of rounded that right there, times e to the negative 18.5 t times sine of 25.65 t alpha. Notice right here again, beta was basically our angular frequency of the cosine portion and the sine portion of each exponential. So here, the only difference, and sometimes people see this, and they're like, oh man, it's exponentials and cosines and exponentials and sines, it's difficult. It's not really. All we had to do was complete the square and then add that basically into how we actually do the partial fraction expansion, and then just start solving like we've done before. So it's really not that bad. Once you practice it, you guys should be doing problems like this, going through this problem. Don't just do the problem and say, I've done it once, I got it, and I understand it. Do it again, then do it again, do it again, do it again. Drill it 5 to 10 times, and make sure that you have that almost in your head automatically. That will help you so much. You never just do a problem once and say it's good. You have to go through and get the skill set down very, very appropriately. It's just like many other things. Like you don't, if you're a golfer, you don't just work that swing and get that swing once. You got to work that swing continuously. If you're playing basketball and you shoot a hoop, just because it just went in and you got that three-pointer doesn't mean that you can do that consistently. You have to work on the skill set of that. It's not just accuracy, it's also precision. Being able to repeat that accuracy over and over and over and over and over. All right, so we're going to take a look now at a couple of problems in which we're actually going to be determining the voltage across the capacitor. This was the substitution method to find the current through the inductor. But later on, we're just going to take the KCL equation, expand it by current voltage characteristic, and it's already in terms of what we're looking for in terms of the voltage across the capacitor. So more on that later. See you then.